Welcome everybody to a new edition of our Let's Talk Science podcast. As we are nearing EMO in 3 weeks in Hanover, this is going to be the last edition before EMO, but once again, we have a very important and very insightful topic for you. Everybody's dealing with saving energy, increasing energy efficiency. And so please welcome Marian Süße of Fraunhofer IWU Research Institute in Chemnitz. He's the head of the Department Factory System Design and Production Planning, and he's going to let you know new insights about energy savings thanks to optimized energy storage systems. Basically, how you can use a customized user-friendly software to select, configure, and dimension these kind of electrical energy storage systems to optimize your energy consumption in the end to reduce waste of this kind of very valuable energy. As usual, please use the questions panel in your dashboard to pose any questions as they come along. We will go through them in the end of Mr. Süße's presentation. And for now, Mr. Süße, the floor is yours, and we're looking forward to learning insightful information. Thank you.
Yes, thank you also for the introduction, and I hope that I can provide some insightful information. Of course, I would like to use the next 15 minutes for introducing a special project, which is called Energy Storage in Production, also on behalf of our colleagues and the main project leaders and initiators, Hans-Martin Strehle and Marc Richter. So we will have a quick insight into the project that is funded by the Federal Ministry of Economic Affairs and Climate Action. And of course, at the end, I will be happy to answer some questions. Typically, I don't like to talk that much about the Institute for an introductory part. However, I think that it's quite a bit important for today's presentation because I want to make sure and I want to highlight that we are coming from an end user perspective. So our institute originates from classical forming, classical cutting technologies. Of course, we develop many more topics and departments like additive manufacturing, IT-related aspects, cognitive production systems, and so on. And of course, also the department that I'm representing, which is factory systems design. So what I want really to make clear is that we are looking at the topic not from a mere software developer perspective, but from a perspective of the end users of small and medium-sized enterprises, of factory planners in general. And of course, we are related to the research focus and area of production systems and factory automation. And our goal is to provide, let's say, efficient production planning and factory planning solutions, and also the appropriate design of energy supply and energy usage in production. So this is quite important to know in differentiation from software developers and other actors. Just as a quick motivation, unfortunately, this is a picture in German, but I will highlight and translate the most relevant aspects. There is, of course, many investigation going on how to use different energy storages depending on different sizes and the general area. What you see right here is an investigation of the colleagues down below. They investigated the current capacity until 2019 for home storage systems, for industrial storages and large-scale systems. And of course, you see quite a small share of the industrial part. And this, of course, is one aspect where what we are addressing with the project, because we want to make sure that the design and usage of such battery systems and storage systems is way easier for industry, because the industry is quite a flexible environment compared to let's say home storage systems. We do have many more and larger load peaks. So the question is, why do we not take the advantage of storage systems in general, and what are the current challenges to overcome? So in general, just to provide a quick structurization and to give you some overall insight into the benefits of storage systems, we just elaborated the main, let's say, areas and scenarios for storage systems and energy storage systems in production. Of course, I think one of the aspects that is the most well known is reducing peak loads during production times when several ovens, for example, are heated at the same time. This typically increases the energy demand or raises some peaks. So we want to use the storage systems for reducing them. Of course, when integrating storage systems very near to machines or into machines and plants, we can also reduce the base load from a whole factory or systems perspective, because we can use them for regenerating energy during several production cycles. Another point, of course, that is quite intuitive is the integration together with local energy sources like photovoltaic plants. So in that case, battery storages or energy storages in general help to make use of the generated energy when it is really needed. So this, of course, then leads to further aspects, which is that we want to generate or build up and design a system that is suitably dimensioned. So in an appropriate way for the demand or the forecasted demand of our energy consumption that we see for the next year, next years, and next time to come. Of course, we do now have many initiatives and also obligations to build up really intelligent energy grids, which require more control of the different energy sources and energy sinks. And in that case, we need battery or storage systems that can be integrated in an intelligent way. And last but not least, there is a growing relevance of DC grids, so really a DC-based infrastructure in factories, which hopefully helps to reduce energy demand in general, but also reduces systems complexity and material demand for electrical power supply. So based on these benefits and expected benefits, we came up with the idea to provide the appropriate tool for designing and controlling energy storages in production. So the main question is, what is actually the overall need for research? And we found out, also in discussion with end users, with manufacturing enterprises, but also with planning companies, that there is on one hand no easy to use design tool, which means that currently a lot of the infrastructure is designed based on experience, based on very rough values, some estimated values with some spreadsheet calculations. So the integration of simulation and dynamic observation is more or less something that only experts can deal with, and the easy to use and easy design of such infrastructure is currently quite hard or not available. And besides that, there is not that much standardization for integrating what we call decentralized energy storages or distribution grids. That means integrating battery storage on the appropriate levels throughout a factory or several factories. So the overall goals of the project are first and foremost to design a tool, which is a design tool for energy storage systems that considers different technologies and can be implemented on several levels. The second one is, and it's directly connected to the first point, that we want to implement algorithms for the operational management and for coupling different energy and power storage systems. And last but not least, we need to make sure that this is working, let's say, in reality. So at the end of the project, there will be a demonstrator based on a machine integrated storage system, which then shows the benefits, but also provides the validation of our overall design tool. Down below you see the project partners. Of course, there are two research partners. We do have one partner that is responsible for implementing the simulation algorithms and developing the interface. Of course, we do have storage technology providers, and this is quite clear that we also need someone with the competence in power electronics. So this is the overall consortium, and I would like to focus on, let's say, the two main use cases we deal with, which is on one hand integrating battery or energy storages on a factory-wide or factory distribution level. In that case, we deal with the aspects of peak shaving and time-shifted usage of the self-produced energy. We hope for that with an appropriately designed battery or storage system that we reduce the factory grid. So we reduce over dimensioning of the energy supply. And of course, in the long-term future, we would provide the appropriate infrastructure to take part in some active energy trading and improvements for power quality throughout the factory. Currently, this is focusing on, and let's say, AC grid infrastructure, but in future, this could also be beneficial for the DC integration. Compared to this, we also deal with a second use case, which is quite near or directly connected to one machine. In that case, we are sure that we may increase the energy efficiency of production machines by providing the option to recover braking energy. So this allows us to integrate machines with a smaller grid connection. And besides that, it is also relevant for providing uninterruptible power supply. This was something that was also a bit surprising to me because I'm not the topic-related expert in that field, but the colleagues mentioned that especially in countries far away from, let's say, Europe and where there are no stable grid connections, providing machines with some uninterruptible supply is quite relevant in several countries. So in that case also we want to deal with active and passive DC integration into the drive system. And in general, both of the use cases consider quite a large portfolio or set of criteria, which is the aging, the power electronics based on very different technologies and scenarios. So to go a bit more into the components of the software system, of course, in the end, there will be a web-based user framework, so it is quite accessible, independent from very, very hard software or systems requirements, mainly browser-based, accessible by the end users. And of course, it is quite intuitive that we need some input data, which is composed by some load profiles, environmental conditions, which are, for example, the surrounding temperatures next to the machines and plants. Of course, we do have production parameters and costs. And then we make use of different models that were already previously developed, but are still developed in the project, where we consider, let's say, physical models, but also data-based models for the machine tools, the energy storage, and the power electronics. And this is then transferred, let's say, in an overall calculation based on the well-established FMI standard. Besides the simulation, there is some parameter variation and optimization. So to configure the most efficient storage system based on different technologies like lithium-ion, like flywheel, and so on. And to provide the, let's say, best storage system from an economic point of view. And this, of course, is also something we are totally aware of. Quite often as researchers, you may be in a position where you just focus on the technological application and just if it is feasible from a technological point of view. But in order to provide a tool that is really relevant for industry and from a business point of view, we do all the parameter variation and optimization finally based on economic calculation. And of course, as I mentioned, it is not just related to the dimensioning and design of the storage system. It also subsequently integrates some management and control strategies for the system that needs to be implemented. So what is the current status of the project? Of course, there are, let's say, two areas we are working on. One is the software development itself. There were quite extensive meetings and discussions with some, let's say, classical requirements engineering. We defined the different use cases and, let's say, the different users of these tools, documented it, and also defined the main requirements from that point of view. And of course, in parallel, we are moving on with the academic research. I would just like to highlight one paper that is soon to be published and has already been accepted, where some methodology and also calculation has been done for the peak shaving operations based on these 4 technologies and with the parameters that you see right here. So as I mentioned, price related, the efficiency from an energy point of view, and also lifetime parameters are considered in that optimization model. And in the end, for the described use case right here, the lithium-ion battery was, let's say, the winning candidate. So in general, we are, let's say, in the mid of the project. And this is also what I would like to highlight right here. So the project started at the beginning of last year. We are quite soon finishing the design tool concept. And in 2024, we will close with the implementation of the algorithms and also with development of the use case storage system. And the project is planned to finish at the beginning of 2025. So that's the moment when the software prototype will be available, and then in the next steps also be made available by the software development partner. And at the same time, as I mentioned, we want to and we need to evaluate and demonstrate the benefits and the results of the overall project. So yeah, actually that's it from let's say quick insight into the ESiP project. And of course, I will be happy to answer any questions if you have further, or if you are further interested into the topic, but also the surrounding aspects of our factory planning projects and energy supply and energy management projects, then have a look at our blog. And of course, you can also reach out to us at any point afterwards. So yeah, thank you for the attention so far. And of course, I'll be happy to answer your questions.
Thank you, Mr. Süße, for these insights. Once again, if you have any questions, feel free to put them in the questions panel on your dashboard. Meanwhile, I would have a couple of questions, if I may. So the one is certainly, everybody's discussing about all the nice ideas to increase energy efficiency and reuse energy. How about the cost? I mean, in the end, I know very good and smart solutions, but usually they're dead before they're implemented because somebody says the cost is not worth the effort. What is your experience here?
Yeah, from an experience, of course, there was some mindset change during this and the last year. We all experienced it, since energy costs and supply costs were quite high, and this also raised the question of, let's say, the relevance of what is called resilience or independence from some energy supply grid. So let's say our project partners and also the industry partners, they mentioned that of course there's always the major goal of efficiency and costs from a business perspective, but they found out that in a moment when there are no more resources available, that means also energy is not available, you need to have some backup, meaning local power or energy supply, which also leads to the question of battery or energy storage systems. Related to the storage systems or costs of the storage systems, I would say it depends definitely on the use case. So the use cases that were investigated in the paper that I mentioned, they are presented quite clearly. One of the outcomes is also, let's say, a lookup table where you can investigate if the costs per kilowatt hour will be higher for your overall factory systems or lower, depending on the load peaks, the amount of load peaks, and also the size of the battery system. So I would say the awareness for the benefits of storage systems has increased, but I would not say that there is generally a reduction in costs currently. So it really, at the end, as always, depends on the use case.
Mentioning that, did you or did your partners somehow investigate into I would call it second life storage systems? So especially batteries coming from cars that certainly have reached the end of life for the mobile application, but still have a pretty good life expectancy in stationary applications. Can you say anything about how this is developing?
Yeah, of course, this is not in the focus of the project, because at the end they different, or second life batteries in that case would just differentiate due to the parameters of, let's say, costs and aging or lifetime or rest of life cycle. So of course they can be evaluated with the tool like any other energy storage system. But of course, with from our network, we do have, let's say, also local powers who provide quite extensive methods and also analytics tools to investigate batteries that were used in mobile applications and that are now part of manufacturing enterprises or battery farms. And I really realized that developments were definitely increasing during the last 1.5 years. So we do have partners that just focus on, let's say, some AI-based analysis of the rest of life of battery systems, which hasn't been or wasn't that successful and relevant until, let's say, 2021. But during the last 2 years, they really got a huge increase on requests and cooperation offers. So I think that this is a very clear scenario, and the main question is let's say the reliability of the forecast for each of the battery packs.
All right, thank you so much. I don't see any other questions here, so thanks for everybody who listens in. Thanks to you, Mr. Süße, for being with us and sharing your knowledge. And as I mentioned, this is the last edition of our podcast before EMO. I just look at the clock on the EMO Hannover website, and it says 18 days, 21 hours, 6 minutes and 30 seconds. So we are all getting enthusiastic. And then see you in Hanover. Have a good time until then, and safe travels to Hanover. Bye-bye.
Thank you.